morning, good afternoon, wherever you may be in your day. Thank you for choosing to follow from part 1 to part 2. Thank you. All right, so we're going to do the math here, and I know what you're thinking. Boy, Dr. Wirgo, there was a lot of blah, 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 blah on that last thing. What's it look like in practice? Because you really just confused the living you-know-what out of me on that second slide. Okay, so let's see if we can demystify this and make it a little bit easier. Okay, so let's take a standard heat flow calculation, and then we'll do one that's a little bit trickier. So, without further ado, let's take a look at these things. Okay, so number 1, I'm going to call these Q-type questions, because there's going to be about 5 or 6, depending on how you want to count it, types of calculations we're going to do in this thermochemistry chapter. And the good news is, they're fairly straightforward to recognize which is which if you learn your Qs. They're not trivial mathematically, and they're not trivial conceptually, and I would never say such a thing. But we can identify which is which. So the key for these, what I'm going to call Q-type questions, or these heat flow questions, is we're going to see a change in temperature. That's our giveaway. That's what we're looking for. So I know I'm going to do these right now, and we're only doing this, and then we'll do another video with a different type, we'll do another video with another type. But as I go through, I want to sprinkle in what our Qs are, so when they get mixed up on homework, or they get mixed up on a test, you can identify which attack to take. Okay, so calculate the energy needed to brew a cup of coffee, because you need a coffee, when the temperature of 280 milliliters of water, that's what they say a serving size for coffee is, needs to be warmed from 20 degrees Celsius to the perfect brewing temperature at 85 degrees Celsius. So how much energy do I need for a standard cup of coffee? Okay, so as always, let's just break this down. Milliliters, temperature change, energy needed, that's my question. So I got a couple of these things, right? So again, let's say this is Q and delta T. What I want you to really do with these Q and these delta T's is do a couple of things. Is how many Q's do I have? So number 1, realize delta T means Q. Number 2, how many? And you know I like to spend time on how to break down the word problems. We need to know where to start, otherwise we have no hope. So I spend more time up front, admittedly. So again, this might be a straightforward question, but I want to break it down piece by piece on how we go about it. So, how many things here are changing temperature? That's what I mean. How many things are, because again, Q is change temperature. How many things are changing temperature? Well, energy, blah, 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 cup of coffee, blah, blah, blah. The only thing we really talk about in here is what? Water. So we got 1 Q. Second question is, for each Q, is it a pure substance, such as water? Is it an object, such as a calorimeter, which we haven't talked about yet, so it's not? Or is it a chemical reaction, such as the heat of fusion? Again, haven't talked about that yet in the video, so it's not any of those. But again, this is the process we're going to go through. We're going to layer onto this framework. So what have we decided? We have decided there is 1 Q, and water is best defined as a substance, not an object like a calorimeter, and not a chemical reaction like, I don't know, water on fire or something. So if that's the case, for a substance, it's Q equals Cm delta T. For an object, Q equals C delta T. And for a reaction, it's going to be Q equals N delta H. We haven't got there yet, but I'll put it up there just so you have it all in one place. And then, if we only have 1 Q, we just use this formula. If we have multiple Qs, remember that we cannot create or destroy energy or matter in the universe, so the sum of all the Qs has to equal 0. So, that's where we're going. That'll be the next example, but let's take this layered approach. So, we have one thing. It's a substance, Cm delta Q. We're solving for the energy needed, so that is which of those symbols? Energy needed is going to be heat as a measure of energy. None of those other things are. And then we got to look at this piece by piece. It means we need everything else. Did the problem give me the specific heat of water? And the answer is no, it didn't. But, and I will say this, when we get into multiple Qs, these all need to match. So I'm going to say water, 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 just to reinforce good principles here. So do we have the specific heat capacity of water? No, but specific heat capacities are intensive properties. We could look them up in the book, or we could even remember that Dr. Wirgo said A calorie is defined as the specific heat of water, and a calorie is equal to 4.184 joules. So this is 4.184 joules per gram degree Celsius. M is mass, and they didn't give me a mass of water. What did they give me for the amount of water? They gave me 280 milliliters, but we have to realize the density of water is 1 gram per milliliter. So all those little things we talked about, they're coming back. I like this about chemistry. We bring in ideas. You have to extrapolate, reapply. So if it's 1 gram per milliliter, 280 milliliters equals, we divide by 1, 280 grams. Or actually, we multiply by 1, sorry. 280 grams. A milliliter is a gram. And then lastly, my change in temperature. And we want to look at this right. Although the energy required is an absolute value, we like to look at these Q calculations, and if it's positive, so if Q is positive, this means energy went into the system. So this would be endothermic. Endo enters. If Q is negative, this means energy left, exited, exothermic went out of the reaction. So again, reinforcing vocabulary. All right, so delta T is always final minus initial. So what's my final temperature? If I'm warming at 285, that's my final. That's my initial. So we have 85 degrees Celsius minus 20 degrees Celsius. And from here, it's literally just plug and chug. Grams goes away, Celsius goes away, so my answer would be in joules at the end. And I got, let's see, what my sig figs be would be 3.76100 joules. Or, if we wanted to make this a little bit more how you'd normally see it, there are 1,000 joules in a kilojoule. Sorry, that's a 3. Terrible handwriting. 1,000 to 1 either way. And this would be 76.1 kilojoules of energy needed to raise 280 milliliters of water, 65 degrees Celsius, or brew a cup of coffee. Hopefully that's pretty straightforward. I know I spent a lot of time on how to tackle the problem, but again, you get, a lot of times the setup's the hard part. The rest of it's just, as I like to call it, mathematics. Let's do one with hard mathematics. Also pretty straightforward reaction. A 9.782 gram copper bar with a capacity of 0.384 joules per gram degree Kelvin at 12.2 degrees Celsius is dropped into 75 milliliters of 39.5 degrees Celsius water. What's the final temperature of the bar? And you're going to see in this chapter a lot of these things. Assume perfect heat transfer between the bar and the water. Assume that no energy is lost to the surroundings. Assume perfect heat transfer, etc., etc. Because in reality, when you do this, some heat's going to radiate out to the surroundings, right? Unless you're doing it in some high-tech vacuum. So you have this issue of bleeding of temperature. Now, in reality, we can correct for this experimentally, but from a in-class on a piece of paper standpoint, we can't. So you're going to see a lot of these caveats, and to be honest, for most of these caveats, you just ignore them. All it's saying is you can do the math. You can put an equal sign in and it's A-okay. So, what are our questions? Is this a Q problem? Yes, I'm changing temperature. Now, they didn't give me the delta T, but they're asking me what's the final temperature, and they give me the initial temperature, and they give me 2 temperatures. So all of these things tell me this is a Q-type problem. Yes. Second question, how many things are changing temperature? And I think if we read this closely, it's pretty obvious. We have 2 things changing temperature. We have the copper, we have the water. So, Q copper plus Q water equals 0. Again, we can't destroy or create matter or energy. So the sum of all the Q's, one of them gains the heat, one of them gives the heat. It's a yin-yang thing, Jedi, Sith, light and dark, good and evil, however you want to look at it. One thing gains the energy, one loses the energy. So I'm going to rearrange this just to make life a little bit easier for later. I'm going to put that negative sign in now. I'm going to move one to the other side. And then, is copper best thought of as a pure substance, an object like a calorimeter made up of a bunch of stuff, or a chemical reaction? Well, copper's a substance. Good. Cm delta T. And I'm going to put copper, copper, copper. On the other side, is water best thought of as a substance, an object made of a bunch of things, or a chemical reaction? Water's a substance. Okay, good. You're getting used to this, I hope. Cm delta T. Water water, water, water. And honestly, we've done all the hard work now. The rest of it's just plug and chug. So, do we have a specific heat for copper? Yep, they gave it to me. 0.384 joules per gram Kelvin. Do I have a mass of copper? Yep. Is grams okay? Does grams match grams? Yep. Why did I ask that? Because we got to make sure. Always look at your units. Change in temperature. What's my final temperature of the copper? I don't know. That's what we're looking for. Okay, so I'm going to put T final here. What's the first temperature of the copper? Ooh, that one I know. 12.2. Is it okay that that's Celsius and that's Kelvin? Yeah, we got a Dr. Virgo. In the last video, I had 273 both sides, Kelvin, Celsius interchangeable. Matter of fact, let's just make that Celsius so we feel better about it. Good thinking. All right, other side of the reaction, math, and I clearly didn't space very well. Specific heat capacity of water. Hey, we did that like a minute and a half ago, Dr. Virgo. It's still 4.184. Awesome. Good for you. Joule per gram degree Celsius. Our mass of the water, 75 milliliters. Hey, we also did that 2 minutes ago, Dr. Virgo. A milliliter's a gram. Just put 75 and be done with it. All right. Sounds good to me. My final temperature of the water? Nah. All right. And what's the first temperature of the water? Ooh, we got that one underlined, 39.5. All right. The trick here is what? We have to realize that the final temperature of the copper bar is the exact same as the final temperature of the water. The copper is going to go up, and the water is going to go down until they meet. So, I'm just going to drop the T. I'm just going to use T and solve for that. We'll make it simple. Best thing to do is multiply those together and then through. So 9.782 times 0.384. The rest of this is just math. It is 3.756 T minus 45.83 equals negative 313.8 T plus a negative times a negative. 1,200, 395. Now this is like where we set the two lines equal to each other the last couple weeks in lab. So we're going to add 45 to both sides. We're going to add 313.8 T to both sides. And we're left with, on this side, 12,441. And then on the other side, 317.6 T. Divide both sides by 317. And I get a final temperature of 39.2 degrees Celsius. At this point, we need to do what? So divide both sides by 317.6. And notice I showed all my math steps to make sure I didn't mess up. Do that. I know it takes a little more paper, but it avoids silly mistakes, and we get right answers. So we know that the final temperature has to be between 39.5 and 12.2. So does that pass the common sense check? Sure. Next thing is, boy, it's really close to the water, and the copper moved a lot. Does that make sense? Well, we have a lot more water than copper, and water has a much higher heat capacity than copper, meaning it will maintain temperature 10 times better. If you look at that number, actually it's over 10 times better. So does that make sense then that the water barely moved and the copper moved a whole bunch? Sure. We got water can hold 10 times as much heat, and we have, 8 times as much material. So sure, put those two things together. That absolutely makes sense. Thank you so much. This is the process. The rest of it's laying out the math and doing the math. Just stick to the course. Change in temperature is Q. How many Qs? Is each Q a substance, an object, or a reaction? We'll pile those last two on in the next set of videos. Thank you.